Has anybody looked at the Chem Compact? If you look at the Chem Compact, then our book only has a few. Our book in Chapter 8 has the combination, decomposition, single replacement, double replacement. If you look in the Chem Compact, which I don't have a copy of, but there's a lot more categories there, right? There's the AX plus water and whatever, many different categories. But the way they organize it is, I think the way all these are organized is not so easy to analyze, because are you missing some? You know, even if we look in the Chem Compact, which has a lot more categories of reactions to memorize, are we missing some? And the answer is yes, we're missing some. I mean, if you look at, for sure, if you look at Chapter 8, you're going to be missing a lot of chemical properties. Chem Compacts, you're going to be missing a lot. And so what I did was, this is why I'm doing a different approach. I'm doing a different approach because I just want to can those, and we're going to take a more general approach to it. And so on one extreme, in order to figure out the chemical properties of HCl, you'd have to take HCl and react it with every single substance around. So for example, let's react it with a table. Does HCl react with the table? Let's react it with sugar. Does HCl react with sugar? Let's react it with this chemical, that chemical. And so we go down the list. Well, how many chemicals are there out there? That millions upon millions upon millions of chemicals out there. And so you're going to be testing those individually. Does that make any sense? And the next thing is, okay, you throw it in one of these patterns, but if you throw it in one of these patterns, that's not comprehensive. And so this is why we want to broaden the categories. And so if I'm interested in HCl, I look for 3 chemical properties. What 3 chemical properties are they? I look for redox, I look for metathesis, and I look for acid-base, and then I have it pretty well covered. You know, that's it. And so in order for this, you know, if I ask you chemical properties, the first thing I'd ask is, hey, this consists of ions. So metathesis, you know, one way of thinking about metathesis reactions are favorable ion combinations. And so I think, what ions does H plus like? H plus likes a lot of ions. All the ions on the base side of the acid-base chart, it likes. And so we could see that here. And so H plus is an acid. And so we could think of it as acid-base, or we could think of it as an ion in terms of metathesis. So here, H plus, aka hydronium, we'll talk about this more when we get to acids, but the ions that it reacts with would be all these. All these bases here react with H plus. There's an easy way to use this chart. The easy way to use this chart, which we'll see, is this. So if I have H plus, which is also known as hydronium. It turns out H plus is you know, it's tiny, it's a proton. It's very reactive, so it immediately attacks water to form this species, which is hydronium. So this is H plus in water. H plus in water will react with any base stronger than water. And so if I look at the base that are stronger than water, it reacts with all these. And so H plus alone will react with everything down here. However, H plus will not react with any base weaker than water here. And so this is a quick way to test. So for example, if I have H3PO4, H3PO4 will react with any base stronger than H2PO4 minus. So it will react with nitrite, it will react with fluoride. However, H3PO4 will not react with any base weaker than H2PO4 minus, like sulfate, trichloroacetate. And so you don't have to know this now, but eventually we can see quite rapidly, when we're looking at acid-base properties or ions, we can see quite rapidly all the species. You know, as long as it's weaker than this or stronger than that, we can predict what's going to happen. And so rather than test these individually, we just say, it reacts with any base stronger than water, which is a lot of things out there. Well, that's with H+. So H+, there's some overlap there because H+ is acid, and this would be acid-base type reaction. All right, then we look at chloride. What does chloride react with? Chloride, well, actually, let me go back and talk about this. Hydrogen's special. It's a cation and it's an acid, and so we can use this acid-base chart. Chloride, we can look in metathesis. If we look at metathesis, what ions does chloride like? Well, we go to the solubility rules. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So what happens when a chloride ion encounters a silver ion? Do you know what happens? Did I show you a video of this? It's called precipitation. So let me show you this on YouTube.
When moderately concentrated solutions containing silver ions and chloride ions are mixed, the resulting solution is supersaturated with silver chloride. A precipitation reaction occurs until the system reaches equilibrium.
All right, there's some fancy jargon
In this
there.
model, the red and white molecules are water. Chloride and silver ions, gray and green respectively, are in solution. When they encounter each other, they bond and bind with other silver chloride molecules that have precipitated from solution to form the solid.
All right, so what happens is silver ions like chloride, and so they'll come together. That's a favorable ion combination, and they come together to form a lattice of silver chloride. Is what that was, and so that's why I said not molecules. It's forming a lattice, and so you have smaller crystals growing into bigger crystals. Basically, that's it. And so that's one. That's different because did you see this? The silver ions actively bonded to the chloride. If you have sodium ions and chloride ions, do they actively come together to form a precipitate of sodium chloride? No. They're apart. They're apart until the water evaporates. The water evaporates and the pool gets smaller and smaller, and eventually they're forced to come together. That's the only time when you're going to get salt is if all the water evaporates and there's no more space available. Otherwise, they stay apart from each other. That's not a favorable ion combination. So a favorable ion combination actively comes together and reacts. Okay, that's what we're looking for. And so chloride will react with silver ions. What else will it react with? Well, we know that chlorides, bromides, and iodides are all soluble, which means that it's not going to react unless there's silver, mercury 1, or lead 2 present. And so I already know that HCl is going to react with anything that contains silver ions, lead 2 ions, or mercury 1 ions. It'll react to form a precipitate. And so those are the metathesis properties. Then we go on to acid-base properties. As far as acid-base properties, then we know, well, H+, that's an ion. It's also an acid, so we already have that covered. That's why we looked at the acid-base chart for that. Let me bring up the chart again. Again, this hydronium, which is H3O+, is the same thing as H+ in water. And so we see what ions it reacts with. So that's H+. But in terms of acid-base, chloride is also a base. But one thing to note is this. HCl is a very powerful acid. So what does that mean for chloride? It's a very weak base. In fact, chloride is so weak, we call it pretty much neutral. So for example, let's say you had too much stomach acid. You ran out of antacids, but you have table salt. We got table salt, and I saw this table. Oh, chloride is a base. Could you use the table salt to neutralize your stomach acid? No, because chloride is too weak of a base. We don't really consider it. In fact, the only acids that chloride will react with have to be stronger here. And there's something tricky, much more advanced about this table, which we might talk about it or might not. Maybe wait for Chem 1A to talk about it regarding this table. But it turns out that all these here are incredibly weak bases. So weak that they're often thought of as not being basic at all. Likewise, with conjugate relationships, the conjugate acid, that is, these are the powerful bases here: methide, hydride, oxide, amide, sulfide. All these are very powerful bases. Therefore, their conjugate acid is incredibly weak. In fact, these are so weak, we really don't consider them acids. For example, hydrogen gas, do you really consider that an acid? No. Methane gas? No. So if you're going to try to neutralize a very alkaline solution by bubbling methane, good luck, because it's just not going to happen. These are just too weak to really be considered acidic. Well, if they're too weak to really be considered acidic, why are they even on here? Well, they're on here because, sometimes people work with more exotic species. In order to form methide, you need an extremely powerful base. And there are superacids and superbases that are, that go down here. Superbases, and then there's superacids that go up there, which we aren't going to talk about. In fact, over at USC, it was like maybe 4 or 5 years ago, there's a professor there, Professor Ola at USC. He won the Nobel Prize for his work on superacids. And these superacids are used to do some unusual chemistry. Like one of the things that they were being used for is the formation of synthetic gasoline by using superacids. But those are kind of exotic. These are kind of exotic too. Amide's common though. Oxide's common. Actually, hydride's common. Methide is not. You can buy hydrides and this type of stuff. Well, anyway, chloride is just too weak. We don't really consider it. Even though it's on the chart, you might consider it. We don't consider it because we just have that registered in our mind. Table salt's not effective at neutralizing acid, as more of a descriptive sense. And so that takes care of the acid-base chemistry. And then finally, we look at, for HCl, we look at redox chemistry. Redox. And so this is where we left off. We were talking about redox. Now, how do you get a feel for redox? Well, we have oxidizers and reducers. Did I talk about oxidizers and reducers already? Oxidizers are the electron poor or electron rich? The electron poor. Oxidizers want to take electrons. So all the species on the left here are taking electrons, plus 2 electrons, plus 2 electrons, plus 5 electrons. Do you see that? All of them are taking electrons. Reducers have electrons that can be lost, that aren't terribly difficult. Strong reducers have electrons that can be easily lost. Weak reducers is tougher. And there's a conjugate relationship here. Fluorine, does it really want electrons? Okay, I think this is where I left off. Yes, fluorine really wants electrons. Fluorine is what we call the most powerful oxidizer on this chart. And so how much does fluorine want electrons? You got to get a feel for that. How much does fluorine want electrons? It's hard to get a feel for that, but you might relate it to something like chlorine. How much does chlorine want electrons? chlorine, is it very reactive or not that reactive? Is it stable or reactive? Chlorine. It's stable? Are we talking about, okay, now there's a difference between chlorine versus chloride. Chloride is relatively stable because, well, it does react with silver, lead, and mercury, but it doesn't really react acid-base, and we'll talk about redox. Chlorine, on the other hand, is very reactive. If you filled this room up with chlorine, you'd know it. This would be a green gas. It's very corrosive. And it'll start to cause some damage. And so chlorine is pretty reactive, and so up here, and then you got to get a feel. You know, it's hard to get a feel without knowing some stories. Like, for example, hydrogen peroxide. Do you know any stories about hydrogen peroxide?
Stories?
Yeah. Stories meaning, you know, how reactive is hydrogen peroxide? I know we deal with household hydrogen peroxide. It's not that big of a deal. It's like 5% or 2%. Right, but if that were 50% hydrogen peroxide, you wouldn't want to pour that on a cut. If it were 50% hydrogen peroxide and you pour it on your skin, it might actually catch on fire, right? Potentially. And so we got to watch out because, you know, hydrogen peroxide, it's like other stuff. You know, if something can burn, then it's going to burn brighter in hydrogen peroxide than in oxygen because hydrogen peroxide is a much more powerful oxidizer than oxygen. If paper combusts in oxygen and air, then paper will easily combust with hydrogen peroxide. So that hydrogen peroxide hits that paper. You don't need a spark or a match. For example, here we'd need a match to ignite it. In 50% hydrogen peroxide, you may not need a match to ignite it. You pour this on here, it's going to ignite by itself. You know, that kind of thing. And so we get a feel for this a little bit. In fluorine, let me tell you how reactive fluorine is. You know, is stainless steel very easy to oxidize? Stainless steel is very tough to oxidize. It holds onto its electrons more tightly than iron. Iron, it's a lot easier to oxidize. You know, the electrons are a lot more loosely held than stainless steel. And so there are different grades. You know, there's like surgical grade stainless steel and food grade stainless steel. The lowest grade, you might see some rust. You know, the stuff that you get for your kitchen. It might start to corrode a little bit. You don't want it to rust, but it might. You know, food grade has to be, if it's going to be in contact with food, it has to be an alloy like 300 or higher. Otherwise, it's potential for corrosion there. But anyway, does stainless steel burn? You know, let's say you ran out of firewood, but you have some scraps of stainless steel, like from your old refrigerator. You want to throw those in the fireplace? No, because if you try to burn them, it's not really going to burn. It'll discolor and start to oxidize slowly, but it's not going to burn. Not unless you had,
Steel wool burns.
Steel wool burns, but steel wool is made out of iron. It's just iron. Iron. All metals are electron rich, and so all metals will be easy to oxidize. And if enough heat is generated, then it'll be like if you buy a bottle of copper, like copper powder, on it is a warning. It's flammable. Have you ever seen that? All metals have that warning. Let me see if there's a label here. Let's just look at that's hard to read.
Right click, open in open picture in tab. break, like it says open a new tab.
No, it doesn't. See if it's your. Here, mate. Do it.
Well, anyway, let me just read it to you. That'll be easier. Combustible. Oh, this is carbon black powder. The same thing is on copper and other metals. When you buy powdered metals, it always says combustible explosion hazard. You know, have you ever heard about like those grain silo explosions or bakery explosions? You know, it's when the flour, when you try to burn flour in bulk, it doesn't really burn easily. But if you get a fine aerosol of flour, then it's explosive. It can react explosive. The same thing with metal powders. If you disperse the metal powder in air and it ignites, it can explode potentially, because metals are what we call electron rich. Oxidizers like oxygen in air is electron poor. So the oxygen wants to take the electrons from the metal. You're going to get what's called a redox reaction, and that can result in explosion. Now, how strong of an oxidizer is fluorine? Fluorine will catch stainless steel on fire, and it doesn't even have to be powdered. It could just be straight stainless steel. And so that's to give you an idea. Well, fluorine's the strongest on the list, but let's take a look at some of the others on the list and get an idea. And so the first thing is we just want to familiarize ourselves with the list. You know, when we see a list like this, you know, some students have asked, and this is a Chem 1A, some students have asked, do I have to memorize it? No, you don't have to memorize it, but you shouldn't ignore it either. Because when we look at a list like this, there are lots of patterns that you can see in here, in this list. And those patterns are really going to help you. Those patterns are going to make you a different level of student, because there are some students here who, if it's not on the list, then they can't answer any questions because, hey, it's not on the list, that's not a fair question, right? But then there are other students who look at this and they go, okay, I see some patterns there. And so if something doesn't occur on the list, they can kind of categorize it. Well, it's similar to this and similar to that, and so they can kind of position it where it would be. And so this is by no means a comprehensive list. There are much more comprehensive lists than this. This is just a small excerpt of some of the common chemicals that might be encountered. Other than this is not so common here, but these other ones are quite common. And so the first step in approaching this is, you know, because it does look overwhelming, there's a lot of data here, is just to see, you know, what the species are. You know, that way we have it registered here. So if we've seen, okay, now we're dealing with H plus and we're dealing with chloride. Have you ever seen H plus and chloride on this list of redox agents? Well, if you've never seen the list or you've never really looked at the list, then you might not be able to answer that. You know, but if you've seen the list and read through it, then you might remember that, yes, H plus and chloride do occur on this list. And where roughly is their position? And so let's take a look here. So at the top is fluorine, and so you should memorize this. Fluorine is the most powerful oxidizer on this chart. What that means is it wants the electrons the most out of any of these species here. Okay, the other patterns you might see are this. Okay, we go from fluorine to chlorine. Chlorine is a weaker oxidizer. Can you think of why it might be a weaker oxidizer? So fluorine, chlorine, then bromine's down here. Do you see bromine? So this is one of the patterns that you might see if you've seen the chart multiple times. You know? But the pattern goes fluorine, chlorine, bromine. Where do you think iodine is? Even though you don't see it, yeah, we can predict it's going to be even weaker yet, right? And so those are the types of things, you know, more in-depth knowledge of this will bring. Although it doesn't really get to the chemistry, it's just being able to make simple predictions like this.
Isn't it because when you go down from fluorine down, it gets less, I guess, strong as an oxidizer?
Yeah, it gets less strong. There are structural reasons for it to get less strong. The biggest reason it gets less strong is because of the size. As the, you know, fluorine's the smallest, and then it goes bigger and bigger. As it gets bigger and bigger, it has less ability to attract electrons to it, and so it becomes less powerful. But you know, those are other ways we can understand this that are beneficial. But initially, this is what we'll do here for fluorine. Also, what else likes electrons? Fluorine, oxygen, nitrogen, all those gain electrons. So, for example, if we have fluorine, how many electrons does fluorine want? One. It's the whole family: fluorine, chlorine, bromine, iodine. All those want one. Oxygen wants 2. Now this is O3. O3 is called ozone. And so ozone is look at the rank. Ozone's up here, O2's down here. Ozone is more powerful. And so ozone's much more reactive. In fact, you feel it. In this room, do you feel the oxidizing power of O2? You don't in this room, but I'll tell you, you know, over the Earth's history, you know, the atmosphere has changed, you know, from more of a reducing atmosphere to more of an oxidizing atmosphere. It's shown in the rocks there. But anyway, we don't feel it because we're used to it. But if we filled the room instead with ozone instead of O2, you would feel it. Your eyes would be burning. Your lungs would be burning. Everything would be burning because ozone is much more powerful oxidizer than O2. And ozone, okay, do you know what the charge on each oxygen is in ozone? It's 0. And so over here we go O2, well, it's 0 there as well. But here, do you know what the charge on oxygen is in water? -2. And so one of the oxygens out of the 3 gain 2 electrons to form O2 minus. Well, O2 minus is not that stable. You've seen O2 minus in the acid-base chart. O2 minus is a powerful base, and so it's not so stable compared to water. You know? And so this is the reason why we have the H pluses there. The H pluses are to stabilize the O2 minus to form water, which makes it much more stable than O2 minus alone. All right, we did talk about this. This is kind of like the bi or disulfate. Let's skip that. What's this one here? Hydrogen peroxide. What's the charge on oxygen and hydrogen peroxide? It's actually minus 1. Hydrogen's +1. And so if I have 2 oxygens of -1, then each of them want to gain 1 more electron to form oxygen at -2. And so this is what we have going on here. And so all these make sense. Oxygen wants to end up with 2 electrons, so this is what we got going. This one, did I talk about the peroxide bond in this? Maybe not. That's not important. How about this one here? Permanganate. So what's oxygen here in permanganate? I have 4 oxygens. Each oxygen is -2. So -2, and then that's going to oxygen over here. This oxygen is -2. So in this case, the oxygen doesn't change. On the left, it's -2. On the right, it's -2. So what's taking the electrons here? It's not the oxygen now. It's the... Well, what is it? Because permanganate has an extra electron. So why is that electron poor? Permanganate has an extra electron. How can that be electron poor? And so do you remember how I wrote these out? I wrote O with a 2 minus, O with a 2 minus. Can you write it out for permanganate and tell me what the charge on manganese is? I'll give you a minute to do that. So what was the charge on manganese? +7 is correct. +7. Did everybody get that, or couldn't figure it out? +7. Okay, the way I figured it out is we have how many? 4 oxygens at -2. And so the total negative charge is -8. And then we have 2 manganese. Manganese is variable charge. But we need to figure out the total positive charge must be +7, because +7 plus -8 gives us a -1. MnO4 minus, this minus has to match this. There has to be an imbalance of charge in order to create an ion. And so if this is, not plus -8, -4, actually -2 times 4, that's only 1 manganese, sorry, is -8. This is +7. There's just 1 manganese, and that manganese must be +7. All right, is that the common charge of manganese? No. If you look at the Chem supplement, you'd see the common charge of manganese is +2 and +3. So this +7 stabilized. This +7 stabilized because of the oxygen. So sometimes we don't write this +7. Sometimes we write it as a Roman numeral 7 to indicate that it's not a free stable ion like manganese 2+. Manganese 2+ alone is no problem. Manganese 3+ alone is no problem, but manganese +7 is a problem. It cannot exist alone. It has to have these oxides around it to help stabilize it, otherwise it won't happen. And so this is sometimes why we write Roman numerals in this case rather than a free charge. In the name we always write Roman numerals, whether it's +2 or +3 or +7, it doesn't matter. We write Roman numerals in the name. But for the formulas, it's a different story. Anyway, can you see why this is an electron poor? It's not because of the negative charge, it's because of the +7 charge on manganese. That makes it electron poor. That makes, this is called what, permanganate? That makes permanganate a powerful oxidizer. So all these species here are powerful oxidizers. Fluorine, ozone, hydrogen peroxide, permanganate. Even this one, what's this one called? Lead 4 oxide, powerful oxidizer. Chlorine, powerful oxidizer. What's this one below chlorine? Dichromate. What do you say? Powerful? Is it really a powerful oxidizer? This has -2 charge. That's 2 extra electrons. How can this be a powerful oxidizer? Because it's where the -2 charge occurs. Where does the -2 charge occur? -2 charge occurs on oxygen. Now when we, okay, what we have to do is we have to evacuate, and then we're going to go out on the lawn over here. So just gather your stuff.